Welcome to 5.3, solving trigonometric equations. This is part 2. I had a visitor stop by my room, so we're going to pick it up at problem number 46. And here we were to be finding all solutions of the equation from 0 to 2 pi algebraically. And up until this point, where we've been solving equations, up until number 46, all of our equations have just been in one single trig function, so cosines or cotangents, sines, tangents. But now we have secants and tangents, and a lot of times I've seen people just rush to go to sines and cosines on this. But the reason we go to sines and cosines oftentimes is because they live together in a Pythagorean relation, and yay, secants and tangents live together in a Pythagorean relationship. And there it is. The problem with this is I can't turn secant into plain old 1 plus tangent and just forget about the squared. We need these things squared. The algebraic trouble with that is we know, for instance, that 5 does not equal negative 5. But if I were to algebraically say, well, why don't we just square both sides, I turn a not true thing statement into a true statement. So squaring both sides should not be something that we do if we have other options, but I think maybe that's our best option right here. So I'm going to get secant alone here. Secant of x equals 1. I'm going to subtract tangent of x. And now I'm going to square both sides, but that presents some peril. We might get some bad answers here. So this is a case, if you square both sides, you no longer just have the luxury of checking your solutions. You really need to think through those solutions. So anyway, I get secant squared of x equals 1 minus 2 tangent of x plus tangent squared of x when we FOIL. And secant squared can be turned into 1 plus tangent squared. So secant squared is 1 plus tangent squared of x equals 1 minus 2 tangent of x plus tangent squared of x. And let's pick it up from there. Okay. So in this case, I notice I can cancel tangent squared on both sides, and I get 1 equals 1 minus 2 tangent of x. I could add 2 tangent of x to this side just to get it positive and subtract 1, and I get tangent of x equals 0 when I divide by 2. And when is tangent 0? When y on x equals 0. And when is y on x equal to 0? Y on x equals 0 when y is 0. And y is 0 here and there. So from that, since we're just going for solutions 0 to 2 pi, we would claim that, okay, x, now I want to think of that as theta, not to get confused with, because this is really our angle measure here. It's not our side length of the triangles we're talking about. Different x's, this x and this x. This would be when angle theta equals, or x equals 0 or pi. Should we include 2 pi? Not quite, parenthesis there. So this could include 0, but not quite include 2 pi. So it thinks those are our answers. So I'm going to take us back to calculator here, and I've got this original equation. As you can see, here's 1 on cosine, that's secant, plus tangent, and subtract 1. I've taken the liberty of setting my window from 0 to 2 pi, and my y-min negative 4 to 4. And the reason I chose negative 4 to 4 is a little bit arbitrary, but it's because I want to know when this hits 0. That would be solutions. And so based on my algebra here, I'm fully expecting these two solutions to happen between 0 and 2 pi. So let's graph that. and looks like 0. Let's go second calc value 1. Let's check the value at 0. Looks like 0 is, but what about pi? At pi, we're at -2 here. When I put in pi, I get -2. I get a false read on that. Even though algebraically everything seemed okay. Algebraically here, though, everything seemed okay. So what we have to do is, if we don't have a calculator at our disposal, we have to put these values back in and see what happens. So what is secant of 0 plus tangent of 0? Okay, secant, the graph of secant builds off of cosine. It's the reciprocal of cosine. Secant of 0 is 1. What is tangent of 0? The graph of tangent looks like this. That's 0 plus 0 does equal 1. But how about at pi? At pi, secant is down here. That would be -1. Let's do this. Secant of pi plus tangent of pi. 0. Does that equal 1 is what we just tested. Sorry. Does secant of pi plus tangent of pi equal 0? Let's see. Secant of pi is -1 plus tangent of pi. Well, tangent of pi is right back at 0. See, these don't equal 1. Sorry about that. These don't equal 1, but if I was to square both sides, I'd turn that false into that true. So that's the shame of this one. We get a false read on this problem, and only x equals 0 is an answer. If you have to square both sides, you got to pay the price for it later on by checking your solutions. You don't always get a false solution, but you could get 2 solutions and maybe they're both false. So our only solution here is 0. We don't want to square both sides if we don't have to. Okay, so back to problem number 48. I guess not back, forward to problem number 48. Sines and cosines, yay, they live together in a Pythagorean. My thought bubble, which I don't know if I have handy here. Yes, I do. My thought bubble on this one is, well, sine squared plus cosine squared is 1. So sine squared could be replaced by subtract the cosine squared. So this could equal 1 minus cosine squared of x plus the cosine of x plus 1 equals 0. Not great, but better than having a sine squared. Better to have all one trig function. Let's see, we get negative cosine squared of x plus cosine of x plus 2 equals 0. This thing is quadratic. I'm not going to try to factor with the lead coefficient in -1. I'm going to multiply both sides by -1. Cosine squared of x minus cosine of x minus 2 equals -1 times 0, 0. And now I would like to factor. Are there factors of -2 that add up to be -1? -2 plus 1. So either cosine of x is 2 or cosine of x is -1. When is x on r 2 to 1? When is x bigger than r? It is not. When is cosine -1? Well, that's quadrantal. My graph of cosine looks like this. And it hits -1 right there at pi. X equals pi. Do we need to check that? I didn't square both sides. Maybe if time permitted, we'd check it. If we were taking a quiz test or had to be absolutely 100% certain that was right, we might check it. But that should be solid. We didn't have to square both sides. Okay. Here comes a huge issue that you need to be good at when you're in calculus, and that's when we don't have plain old x's here. Got x on 2, 2x, 2x, x on 4, and we're supposed to solve the multiple angle equation. And when it says solve, it means all solutions. We didn't get a 0 to 2 pi, we didn't get a 0 to 360 degrees, and that we're going to assume when they don't ask us that we're going to be working in radians. Okay, I would rather this not be x on 2. I'd rather this just be plain old x. I'm going to say u equals x on 2, and then just solve this way. Oh, well, that seems easy enough. Sine of u is 0. Well, when is sine 0? When y on r is 0, or that's quadrantal. Here's the graph of sine, and it goes on and on forever. It's 0, at pi, at 2 pi, and I bet it's 0 at 3 pi and 4 pi and negative 1 pi, multiples of pi. So integer multiples of pi. So u is integer multiples of pi, or 0 plus n pi. But that's what u is. We need to solve for x. So x on 2 is equal to u. So x on 2 equals n pi. X equals, how do we solve for x? Multiply by 2. 2n pi. Oh, everything happens half as fast. What used to happen in pi, if it's half as fast, that's twice as slow. Now it doesn't happen until 2 pi. This graph would be twice as wide. Oh, I see. All right. So if I call u 2x here, then I'm just going to deal with tangent of u. And you may ask, why do we use u? It is just very, very common. In fact, there are rules in calculus called u substitution. We just put u in for something just to get a more convenient argument here. So u takes the place of 2x. So tangent of u equals negative 1. That is when y on x is in ratio negative 1 to 1. That happens here, 1 to negative 1, and there, negative 1 to 1. So if we were naming this solution, we could say u equals, and since it's all solutions, I'm just going to go back to this one. That's negative pi on 4 plus, I could go revolutions, but notice I could go add half revolution, half revolution, half revolution, half revolution, plus half revolutions. That would be our solution. But this is 2x equals, u is 2x, negative pi on 4 plus n pi. How do we solve that for x? We divide both sides by 2, and we get x equals, that would be, or multiply both sides by 1/2, negative pi on 8 plus n pi on 2, or n on 2 pi. Divide this by 2, divide that by 2. Oh, all right. Let's continue on with this. U is 2x. I want to know when sine of u is negative square root of 3 on 2. That's when y on r is in ratio negative square root of 3 on 2. When does that happen? That happens when y is negative and long in a 30, 60, 90. For instance, negative square root of 3 on 2, negative 1, or negative square root of 3 on 2 and positive 1. So that could be, I could name this angle right here negative pi on 3. So this is u equals negative pi on 3 plus, I can't hit this, I can't say plus a pi on 3 or minus a pi on 3 multiple revolutions. I got to go a full revolution to here plus 2n pi, and then I have to have a second set of solutions. I could go negative 2/3 pi to get to here, or 4/3 to there. Either one is fine, 4/3 or negative 2/3. I'm going to go negative 2/3 pi plus multiple revolutions. But that's really what 2x equals, those. So x equals, divide those by 2. Divide this whole thing by 2 and this whole thing by 2. And I get negative pi on 6, multiply by 1/2 if you like. Multiply by 1/2 plus n pi, multiply by 1/2. Negative 2/6 or negative 1/3 pi plus n pi. If I multiply by 1/2, I get negative 2/6 negative 1/3 plus just n pi. Be a really good time for you to give this one a shot on your own and pause the video. Okay. You may want to turn this into sines, but I'm going to leave it as cosecant. But I am going to say u is x on 4. So this becomes cosecant of u is square root of 2. When is cosecant square root of 2? Well, that's when reciprocal of sine, sine is y on r, this is r on y, is in ratio square root of 2 on 1. That's a 1, 1, square root of 2, 45, 45, where y is positive. It happens right here and right there. These are 45s. And so we could say u is pi on 4 plus multiple revolutions, or 1/4, 2/4, 3/4 pi plus multiple revolutions. But that's what x on 4 is. X on 4 is pi on 4 plus 2n pi, and x on 4 is 3/4 pi plus 2n pi. Multiply both sides by 4, and I get x equals, multiply by 4, pi, multiply by 4, 8n pi's, multiply by 4, or start at 3 pi, multiply by 4, 8n pi. So, a little sneaky there. All right, use graphing calculator to approximate solutions from 0 to 2 pi. So first thing we have to do is make certain that our calculator is in radians. I think we are. I think we looked at that already, but mode, we're in radians. 0 to 2 pi. Windows should go from 0 to 2 pi. Mine is set that way already. I didn't enter 6.283. I entered here just 2 pi. And now I'm going to graph cosecant squared. So here we go. Y equals, clear this guy. Cosecant is reciprocal of sine, so I'm going to go 1 divided by sine of x, close that parenthesis, square that, plus 0.5 times cotangent, reciprocal of that, 1 divided by tangent of x. And then I'm going to subtract 5 here. Now, because I'm subtracting 5, I don't know where these zeros are going to pop up, but I'm going to go ahead and just graph that thing, and then we'll see if we can spot some zeros here, or if we need to readjust our graph. But truthfully, we're looking for where it hits 0. So to be honest with you, I really only care between -4 and 4 is probably fine. I don't need to go any higher or lower. I might want to make that -1 to 1. I just want to see where it hits 0. So let's graph these. There's a 0. Don't care if I don't see that minimum. There appears to be a 0. Looks like we might get a couple more. So, and we're just to round here. Good news, it's all calculator problem. So second calc 0. I'm going to go all the way over to this one to the left. We're going to get to the left of this 0. Looks like we have some symmetry here. Get to the right of that 0 and guess, and we have a solution. X equals, approximate, let's go 3 decimals, 0.515. Second calc 0. To the left of the 0, to the right of the 0. Wow, where'd I go here? Let's try that again. Left bound. Am I not in second calc 0? Now let's do it again. Second calc 0. Let's try that again. Left bound. I was hitting second. Silly. And we get 2.726. And second calc 0. Should be coming down. There we go. Enter, enter, enter. We get 3.657. And one more. Second calc 0. I'm to the left, and I'm to the right, and we get 5,868. So strictly calculator, we're all between 0 and 2 pi. I set my calculator 2 pi, and that's 6.28, so that's definitely beyond. We're definitely within that domain of possible solutions for x, or range of solutions if you like. Okay. Use inverse functions where necessary to solve the equation. All right, so here we have secants and tangents. I'd rather just have tangents, or rather just have secants, but secant squared may be turned into 1 plus tangent squared. So this is 1 plus tangent squared of x plus tangent of x minus 3 equals 0. So let's see, that's quadratic. Tangent squared x plus tangent of x minus 2 equals 0. Does it factor? Tangent of x factors of negative 2 plus 1 minus 2 equals 0. So we get tangent of x equals negative 1. Well, that's no big deal. When is y on x negative 1? That happens right here. That's positive 1 on negative 1, and right here that's negative 1 on positive 1. So some of our answers would be x equals, let's see, solve the equation. So that's all solutions, so we're going radians. I'm going to go negative pi on 4 to here, plus half revolution, half revolution, half revolution, multiple half revolutions, n pi. But this one, when is tangent 2? I know tangent reaches 2. That's when y on x equals 2 on 1. And you might think, oh, that's a 30, 60, 90. But that would have to be an r value of 2. A 1 on 2, that triangle would look like this. Y on x, 2 to 1. This is 2 to 1. This would be like square root of 5. Yikes, it's not a good one. And it could happen over here, negative 2, negative 1. And that's why they say use inverse functions. So I'm going to, we're in radians right now, second quit. I'm going to say, oh, that's when x equals tangent inverse of 2. But I know it happens twice, and they're not going to give me 2 answers for it. Tangent inverse 2 is 1.107. This is 1.107. 1.107. And this would be 3.14 later than that, plus multiple half revolutions. So we got a little bit of rounding mixed with no rounding whatsoever there, but that's what they're looking for. Okay, very similar. Great time to pause and try this problem and feel the reward of getting it done and having it correct before I go through it. I can turn cosine squareds into sines. This could become 2 times, in place of cosine squared, 1 minus sine squared plus 7 sine equals 5. Or I get, let's see, 2 minus 2 sine squared theta. I don't know why I put a theta there. X, old habit. Plus 7 sine x equals 5, and that's quadratic. Let's see, I'm going to group everything on the right so my squareds are positive. So I'm going to add 2 sine squared x, subtract 7 sine x's. Let's see, subtract 2, and I've got a quadratic, and I'm wondering, might that factor? If not, I got a big mess in quadratic formula. Are there factors of positive 6 that add up to negative 7? There are. Negative 6 and negative 1. I can get a negative 6 by putting a minus 3 here. There's a negative 6. And I can get a negative 1 by putting a minus 1 here. Let's see, that's 2 sine squared minus 6 sines minus a sine minus 1 minus 3. Got it. That equals 0 when sine of x equals add 1 divide 2, no problem. Or when sine of x equals 3, don't know about that necessarily. Hopefully you do, but when is sine 1/2? That's a breeze. Y on R. Short y, long r, 30, 60, 90. It happens right here and right here. So we have solutions of x equals pi on 6 plus multiple revolutions and 1, 2, 3, 4, 5, 6 pi plus multiple revolutions. How about sine x equals 3 on 1? That's when y on r equals 3 on 1. 3 on 1, how does that happen? We'd have to have a y be 3 when an r is 1, and that can't happen. So I don't need inverse functions on this. If we went to inverse functions on this, our calculator should slap us, but it would be sine inverse of 3. It says, no, you can't do that. What were you thinking? All right, so this is a couple days we'll be spending on this. Here's our assignment for this semester. You may opt out of that 1 through 4. We're going to continue along with the way we went through first semester. They're good problems, but here's your assignment. I think we'll have a lot of good conversations on this. Come in if you need some extra help. Very important that we get off to a good start in this section. Huge, huge, huge for calculus. We'll probably at the end of the year come back and review solving trigonometric equations as well. Let me know what I can help you with.